Okay, so welcome everyone. I'm Rémi Servien. I'm a French researcher in data analysis. I'm based in Narbonne, and so I'm going to talk about some data analysis methods. I won't go any deeper, very deeper in the mathematical frameworks. But I will give you some basic ideas for four different analysis methods, and I hope after you will know when, why, and how you could use this kind of methods. So a quick summary. First, I will deal with principal component analysis, so PCA. Then with clustering, with partial least square regression, so PLS, and one method of machine learning, namely random forest. And after this talk, you will have a practical applications using the software, the freeware R. You should have received the file to make this practical application, and I will be here if you need any help. I think we will have finished maybe at 4 or 4.5. It depends on how many time you will spend on the practical application. So just feel free to ask questions anytime. I'm not sure I will be able to see if you put your hands up. So if you want to interrupt me and to ask a question, do not hesitate, please. And there is no dumb questions. So I don't know which backgrounds do you have, so maybe I will assume something is known, but it is not. So please ask a question, do not hesitate. And also, if I use an unknown acronym, you should ask me what does it mean or whatever. So I will start with the principal components analysis. So the goal will be to be able to apply and to read principal component analysis. For example, to know when you could or you should use this kind of data analysis method to give you some intuition and a workflow of principal component analysis. So you will have to deal with it also in the practical application. We will have a very simple data set, the wine data set, to show you some basic example with principal component analysis. We will interpret the plots, and so the main goal is to learn the basics of principal component analysis. So when you should use principal component analysis. So if you have a data set with many quantitative variables, so only quantitative variables that are or that could be correlated with each other. And you need to visualize or to simplify your data set in only 2 or 3 dimensions, for example, without losing too much information. Donc, so that the principal component analysis will help you to perform this kind of analysis, and it could be used as a processing step before any clustering, regression, or machine learning methods. That is only a descriptive approach. So it could be relevant to see some global trends, but you won't have some kind of p-values or something like that with a principal component analysis. And it could be used in many applications, such as chemistry, marketing, sensor data, product attribute, or whatever else. So to give you the intuition in 10 seconds. So you have a data set with a lot of variables. So a lot, it could mean 10, but it could mean several thousand or million or billions of variables. And you want to find some components that summarize your dataset X. So principal components analysis will build principal axes that are linear combinations of your original variables. And then we could project the individuals onto several axes of this principal components analysis that could provide you with a clear visualization. So just to give you a little mathematical intuition on the problem. So principal components analysis solves an optimization problem, which is a problem that is here. I hope you see my mouse when I move it. And so it's a search for the vector W, which maximize the variance XW under the constraint that the sum of the weight W are equal to 1. And after, each principal component is a linear combination of the original variables. So for the first principal component axis, so PCA with k equal 1, PCA1, it will be equal to a first weight multiplied by the first variable plus a second weight multiplied by the second variable, etc., plus last weight multiplied by the last variable, with the sum of the weights equal to 1. And you will deal with it for the first component analysis, so k equal 1, then with k equal 2, then with k equal 3, etc. You will have at the end P principal components, but they will be ordered by importance. So you will be able to select only maybe 2, 3, or 4 components and to have a lot of variance, so a lot of information that was in your data set. As I explained, the first axis, so PCA1 is the axis where we have the maximum variance direction. So variance means information. And the next axis are orthogonal directions to the first one with decreasing variance. So the second one is more important than the third one, etc. We built as many axes as the number of variables, so we don't lose any variance, but we could select only the first one and maybe keep 95% of the total variance. And so the weights W are called the loadings coefficients of the variable xg on the components k. So how could you apply principal components analysis? So first, you have to clean the data. We want no missing value, no outlier, and no relevant variables. There are some modify algorithm that could deal with that, but here I will explain the very basic principal components analysis. So you start with no missing value, no outlier, and only a quantitative variable. You could standardize all your variable at the same scale, or at least you could think of it if you need to standardize your variables or not. And then you could run a principal component analysis. So for example, in R, there are a lot of packages that could perform that. It's really quick, so just some kind of matrix calculation. And at the end, you have the principal components for each principal component, so the first, the second, etc. The explained variance explained by each axis. the scores for the individuals and the loadings that we have so for each variables. And you could have some visualization of the different results that we will see after. So for the example, so we have a data set that is called the wine data set. It's a very common data set that is already implemented in R, for example, so everybody could use it as an example. So in this data set, we have more than 100 individuals, and the individuals are the wines, which came from three different cultivars in Italy. We have 13 numerical variables, so that's not a lot, but that's just a toy data set to explain to you the basics of principal component analysis and also the method that we will see after. The variables represent some chemical or physical properties, such as the alcohol that are contained in each wines, the percentage of malic acid, of ash, or other variables such as the color intensity, the proline, etc., etc. And this is a good case study for principal component analysis because in this 13 numerical variable, some are very correlated and some bring the same information. So there is a need for simplification. We don't need all the 13 numerical variables, and we can simplify this data set in less variable. And yes, if you are looking for other toy data set, very simple, there is a famous repository where you could find a lot of data sets that could be used by everyone. So here we have the wine data set, and we perform the principal component analysis on this data set. We take the first two components of the principal component analysis, so PC1 that is here and PC2 here, and we project the individuals, so the wines, on these two component analysis. So you could first see that on the first component analysis, you have 36% of the variance of the information. And on the second one, you have 19%. So with just two components, you have more than 50% of the information of the whole dataset. And if we look at the location of the individuals, we could see that maybe there are some cluster that seems to appear on these two components. So this cluster could mean that some wine share some global trend. Yes, I see that, Alex.
Yes. Hello. I wanted to ask if you could briefly explain what variables are being used as the principal component one. Is it just some variable, or like what exactly is that? What we see in the exact, yes, that, and also like on the y-axis, like what are these?
Yeah, the first components analysis here is calculated as a linear combination of the 13 original variables.
Ah, okay.
Okay, so we will see after all the loadings of the variables, but here they are not plotted, but they are a linear combination of the 13 variables.
Okay.
And here we visualize only the individual, so the wine.
Okay.
And after, that's maybe what you ask for.
Oh yeah.
So in this plot, I had 13 variables, and the arrow in red are the length of the arrow are proportional to the importance of the variable on the components.
Okay, I see.
So, for example, here you could see that on the first axis you have the flavonoids variable
Mhm.
that has a really high weight on the first axis because the arrow is
Yeah.
really high here. And it has nearly the same impact on the first axis that the proanthocyanine and the total phenols.
Okay, I see.
And its impact is opposite than those of the alkalinity and the no flavonoid phenols. Okay, and
Okay, okay.
these three and these two variables nearly have no influence on the second axis,
True, yeah.
where you can see that the color intensity has a very high importance, negative
Hmm.
importance, yeah, and it's an importance that is really linked to the alcohol variable.
Okay. Okay,
And
I see.
yeah, and you could also anticipate the location of the individuals regarding the variable. It means that, for example, this individual here,
Hmm.
it should have a really high value for flavonoid and total phenols and proanthocyanins,
Makes sense, yeah.
but a really low alkalinity of ash and no flavonoid phenols.
Okay, so you can kind of like predict it via this.
Yes, and this one has a high color intensity and probably a low U or diluted wine.
Okay.
So that's the kind of information that principal component analysis could bring you. So for the variables by constructing the principal components, and for the individuals by plotting the individuals on the principal components by plane. One of the difficulty is to choose the number of components that are representative. For example, here we could see that with the first components we have 36 percentage of the variance explained. For the second one, you have 19%, and then for the third one, you have 11%, and then maybe 5% for the last components. And if you want to perform an analysis on the principal components, you have to choose a number of components. You could choose maybe two or maybe three, and but there are different kind of criterion to help you to make this choice. Um, so if you want to interpret this plot, so as I already said, if the individuals are close together, they share some similar profiles. The length of the arrows of the variables is linked to the importance of the variables on the principal components. Yes, the angle between the arrow give you also information about the correlation of the variables. If they are a small angle, so the arrow are really closed, there is a positive correlation, and otherwise it's a negative correlation. As I explained, you could decipher the relation between individuals and variables. And you have the script plot, this one, to look for the elbow to keep the main component. So you here maybe you could see that three components will be enough, or another criterion could be that you have 13 variables. So by random, each variable should explain 100 over 13, so maybe 8% of the variance. So here you could choose all the principal components that are above 8%. So that's give us three variables also. Um, so if you there is some common pitfalls with principal components analysis. For example, if you have some categorical variables, the basic principal component analysis can't deal with it. So you need to practice an encoding to your variable or to use an adaptation of principal component analysis, namely MCA or FEMD instead. If you are forgetting the missing values, you could have some unstable results. So you need to take care of the missing values before principal components analysis. And you need to keep in mind that principal component analysis is a descriptive method, not a predictive one. It's unsupervised, so it won't give you any prediction. And also, you should not confuse the scores that are the value for the individuals with the loadings that are the weights for the variables. Um, so, a brief checklist for principal components analysis. So you need to have only numerical variable. You need to handle the missing value, maybe to standardize your variables, at least to think of it, to choose the number of components using the script plot. Then you could interpret the individual and the biplot plots. And if you do all of that, you will have avoided all the pitfalls of the principal components analysis. And in theory, in principal components analysis, you find directions of maximum variance in your data sets. So in the mathematical that are behind it's an eigen decomposition of the covariance matrix. And you could go deeper, but that's not necessary to apply principal component analysis correctly. And I won't give any details of that today. That's a very common method. So you will have a lot of package in Python, in R, or in any of the software you will use. You will have also a lot of tutorials online that you could use if you want to go deeper in the details. And at the end of the talk, you will have a very simple example to apply on using R. So as I say, it's a very common and old method. So a lot of derivative have been implemented. For example, to deal with outliers or to deal with nonlinear relationships, because here, as I said, the principal components are linear combinations of the first variable. You could also have some sparse PCA with parsimonious results, so with some weights that will be exactly equal to 0, and the results will be more easily interpretable. And of course, there is also other dimension reduction approaches that perform the same kind of results that the principal component analysis could bring you. And you could also look at that to see the difference with the principal components analysis. So do you have any questions? Okay, so now I will give you a brief introduction on clustering. So clustering, it happens when you want to make some group of similar data points. So individuals, for example, the different wine, for the example that we see before, based on the feature, so based on the data sets and the variables that you have. The main goal is thus to discover the hidden structure in your data and to group the similar individuals. As principal components analysis, there is a lot of application and a lot of different methods to perform clustering methods. And here also we will use as toy example the wine data set. And we'll try to make group of wines based on the chemical features. So first, clustering, you could have two different, so supervised clustering. So as I said before, supervised clustering or other approaches is when you have a target variable. So here, for example, you have your data set X, the wine data set, for example, and you already have I don't know, the different cultivars of the wine, and you want to train some kind of model based on this already labeled data. The goal of supervised clustering could be to predict, for example, a label of a new data point. For example, you have a new wine that is analyzed. You have only the 13 variables, the chemical and the physical one, and you want to predict the cultivar of this wine. For example, yes, so as I already said, if the wine type is already known, you could train a classifier and see if you could predict a new wine type correctly. And you also have unsupervised learning. So it works on unlabeled data. So you have only the data set X, and you want to predict if there is some hidden structures, so some hidden groups in your data sets. So here, for example, you have your wine data sets, you don't have any labels, and you want to group similar wines. And after, maybe to see why those wines are clustered similarly in a cluster and analyze this kind of clustering. So there is a lot of clustering algorithm. For example, k-means, hierarchical clustering, and a lot of other one. I will only present here the more simple, but there is a lot of different methods that are based on different assumptions. First, I will explain to you the k-means clustering. So, in k-means clustering, you have a data set and you want to cluster your data into k cluster with the k already chosen. So we will see after how we could choose k. But here we assume that k is already chosen. So you want to assign the data points to the nearest central head and update the central heads iteratively until convergence. So you have k clusters. You choose k points on your data set and you cluster your points to the cluster to the closest of the chosen points. So there is also a mathematical formulation that just a simple criterion to minimize. So it's not really difficult to optimize using any kind of optimization algorithm. And there are some limitations. For example, it's very sensitive to the initial centroid plasma, but there are some methods to overcome that. As I said, it requires predefined number of cluster K. It assumes some spherical cluster of similar size. So if you have clusters that are not spherical, it could be failed, or at least it is not really appropriated, and it could be sensitive to outliers. So there are some mitigation strategies for each limitation. For example, for the initial centroid choice, and but I will not go deeper in this. So first, basic example to explain to you. So here I have a data set in green. Uh, so we could see that we could say that we have projected it in two dimensions using, for example, a principal component analysis. And now we want to cluster these data sets in two clusters. Okay, we have already chosen k is equal to 2, so we want to choose to cluster it in two clusters. So how k-means performs? So first, it randomly choose 2 points to assign the first data point. So here we have a first point that is chosen here in blue, and the second one that is here in red. So for each of the green points, you compute the distance to the blue and to the red, and you cluster the point to the centroid that is the nearest. So here for this one, for example, it will be close to the blue, so it will be here. You could see in the second step that this point is assigned to the blue cluster. So here, each point has been assigned to a cluster. So you could see here we have the blue one, and here you have the red one. And on this new cluster, you perform a calculation to calculate the new centroid. So by performing a means on the data. So here you have the new centroid, here in blue, and here in red, you have the new centroid of the red cluster. And you iterate the first step. So you take all the data points, you perform the computation of the distance. So for each point, for example, for this one, this blue one, you perform the calculation, the calculation of the distance between this blue center and this red center, and you see that now it should be assigned to the red one because it is close to the red center. So it gives you another clustering. These blue points are red, and these red points are blue. And so you could reiterate the different steps. So you recalculate the center of the cluster. So the blue, it moves here, and the red move here. And you reassigned the different points. So you could see that between here and here, there is only, I think, this blue point that became red. So then you recompute the distance between the centroids. Up, you recompute the centroid, and you see that finally between this and this, there is no more points that change of cluster. And so the Kamins algorithm has converged, and it is so it is over. You have your clustering with your blue cluster here and your red one here. So as you can see, as I said before, it could. So here it's a very simple example. So I don't think it depends on the first choice of the centroid, but on a more complicated example, you could have at the end several convergence that depends on the centroid that you choose at the beginning. So a way to don't not be limited by this pitfall is to run the Kamins algorithm several times and to choose the best clustering at the end. So that's a very simple way to cluster a data set in K groups. So you have to choose K before the algorithm start. Another approach to cluster data is called hierarchical clusterings. So it's builds some kind of tree that are called dendrograms to cluster the data. So there is two main approaches, agglomerative. So you start with each point is a cluster and you merge the closest cluster, so the closest point at the first time. And divisive, it's the opposite. So you start with only one cluster and you split one point by one point. You have to choose the distance matrix and the linkage method, but you can choose classical Euclidean distance and a single linkage method. You compute at each step the distance matrix between all points, and you agglomerate the two that are the closest, and you reiterate until the end. So, for example, here you have a hierarchical clustering dendrogram on the wine dataset. So how do you read it? So at the bottom, the number, each number refers to one individual, so one wine of our dataset. And you could see that there are some joints here, for example, so it's a little, but you perform some agglomerative step and according to the distance. So at the beginning, you have, if you perform the agglomerative approaches, at the beginning, you have each point in a cluster. You compute the distance matrix between each points, and you have a smaller value, which means that the 2 points are the closest one. So you group these 2 points in a cluster. You perform another calculation of the distance matrix between all the points, and etc., etc. And you agglomerate every point in a different cluster, etc., etc. And here you have every point that are in only one cluster. So now you have the dendrogram, and if you want to cluster your data sets in two groups, you will cut the dendrogram here, tac tac, and you will have a first group which will be the blue wine here, and the second one that will be the green and the yellow one. If you want to have three clusters, you will cut the dendrogram here, and you will have the blue one, the green one, and the yellow one. So the hierarchical clustering, it gives you some, in some kind of way, more information than the Kamins one, because here, if you choose three groups, you have your three groups, but you could also see that the green cluster is closer to the yellow one than to the blue one, because they merge here before merging with the blue one. And if you want to cut it in 10 or maybe 12 cluster, of course, you could do that really easily. As previously, for the PCA, you have the choice of the number of groups that could be difficult, but we will see after that there are some metrics to help you to make the choice. As I said, the dendrogram shows the hierarchical clustering of the samples. You have all possible clustering with starting with one cluster to the number of individuals, number of clusters. You could choose the number of clusters that you want by counting the branches that are intersected by an horizontal line. And you could also use an elbow method to choose the number of clusters, or there are more sophisticated index. Um, I put some of these index here, but I won't give you any details. So there are the silhouette score, the AIC or the BIC, Davis-Bouldin index, and the many other. And there are also some metrics to compare different index with different number of groups. For example, the accuracy, the inference score, or the round index, which is very common for clustering problems. So clustering is mostly unsupervised, but can be evaluated with labels. There are a lot of clustering algorithms. So before perform any clustering, you have some choice to made. For example, if you already know the number of clusters, you could use the k-means. If you need a hierarchy, you could need the hierarchical. If you have some noise or some shapes that could be different as the spherical one, you could use DBScan. But there are a lot of options, and that's not always as simple, but using a simple clustering algorithm could give you some quick glance at your data. And yes, if you want to test a different algorithms, you could test them on the wine dataset. Do you have any question on clustering before partial least square regression? No. Okay. So as I said, partial least square regression is a supervised method because we already have a dataset X here with P variable, but we also have a target variable or a response Y. So a very common way to try to predict Y using X is to use a linear regression model where you have to compute the coefficients beta with a noise epsilon. But the linear regression model is very simple, but it assumes that the predictors are independent. So the predictors are the different variables that are in X, and that n is greater than p, that means that the number of individual is greater than the number of variables. So if you want to perform a classical linear regression, if these assumptions are made, there is no problem. But problems could arise when your predictors are highly correlated or when you don't have a lot of observation. That could be the case in a lot of omics study, for example. What is the partial least square regression concept? So in some way, it is the same concept as a PCA. So you want to find some latent components, but here you want to find the latent components that maximize not only the variance of X, but the covariance between X and Y. So unlike PCA, where you have only one matrix X for your dataset, PLS components are chosen to be predictive of Y. So that's why it is a supervised technique, the supervised method, because the components are chosen to be predictive of Y. And also it could handle the multicollinearity and the high-dimensional predictor. So high-dimensional means that P is greater than N. So I will first explain the PLS regression with Y is a vector, so where one dimension Y, but Y could also be a matrix with several variables, and it's the same kind of algorithm. So when you perform a partial least square, you want to find latent variables from X that explain both X variation and maximize the covariance with Y. So that's the same kind of spirit than the PCA, but the latent variables are supervised with the relation with Y. And then you regress Y on these linear components. Yes, the partial least square is also the latent variables are such as PCA, the linear combinations of the different variables in X. Donc, for example, if we stick on our wine dataset, we have our 13 variable for or more than 100 wines, and we want to see if we could predict the quality of the wine from this measurement. So in X, we have our datasets, and in Y, we have some measure of the quality of the wine. Then in a partial least square, you have the same kind of results than in PCA. So you could have a plot of the wine score according to the principal component. So here you have the first principal component and here the second one. And you could see that you have the distribution of the different wines, and I've colored it by the different quality. And then you have, as for principal component analysis, the loadings of the variables to see that, for example, on the first principal component, you have a strong importance of the citric acid, fixed acid, and density, and an opposite loadings of the pH and volatile acidity. You have the same kind of result, but you have to keep in mind that it is a supervised method, so the components are supervised according to your target variable y. So as I said, you could also have the same kind of results where y is not only a vector but a matrix, so with several variables. And so the different components are built to explain the variation in X that are predictive of all the Y variables. So they maximize the covariance between X and Y. So for example, if you want to predict several wine properties, from spectral data. You have spectral data for each one, and you want to predict some properties of your wine. You could perform a PLS, a multivariate, multidimensional PLS. So, for example, here, so you could see that. So I made the two plots on the same plot. So you have the different individuals, so the different wines, and the arrows are always, as previously, the variables, and you could see how they are linked to the different components. And you could see that we also have the y variable. Here we have two variables, so the alcohol and the color intensity. So if you want to predict the alcohol and the color intensity that are here, it seems that on the first component analysis, the more important variable are the proline, the magnesium, and the ash, and they are positively linked to the alcohol and the color intensity. And then on the second component, you could see the difference between the prediction alcohol and the color intensity with maybe alkalinity of ash, malic acid, and non-flavonoid phenols that are positively linked to color intensity but negatively linked to alcohol. And the opposite for these variables. So as for PCA, you have the problem of choosing the number of components. Here, I plot only two components, but maybe on the third and on the fourth, you have important information. So this is a choice that is important because if you have too few components, you will have an underfit of your model, and if you take too many components, you will overfit your model. But you could use, as you have some predict target variables, you could use a cross-validation methods to choose the optimal number. So what is cross-validation? It's a method that is commonly used in statistics in different ways. So you split your data set into one training and one validation set. So you split your data set in two sets. You must have an important number of individuals, otherwise it's difficult to split a small number of individuals in two sets. You fit your parcel least square with a different number of components on the training data. And then, as you have your validation set, you could evaluate the prediction error on the validation set of the different model, and you could choose the number of components that is minimizing the prediction error. So, as I said, cross-validation is a useful tool in statistics. Here, in this case, but it is used in various situations. So partial least square, it combines dimensionality reduction because as in PCA you build a linear combination of variables that are more important for the first one and the linear regression. It could work for single or multiple responses. It is useful also when predictors are many and are correlated. And as I said, the components capture the X variation that is more relevant for predicting Y. As for PCA, the partially square approach is a is an old one, so there are a lot of derivative version. For example, PLSD partially square and discriminant analysis is a supervised version of PLS that is specifically adapted for classification tasks. There are also exist as for PCA some sparse versions that produce sparsity constraints to select only the most relevant variables. There are also adaptation to deal with non-linearity because partial least square, the basic one, is a linear method. And there are also different methods to perform multi-block PLS that could be useful if you have different block of variables. For example, it's very common on omics analysis where you could have a block of uh, metabolomic data, a block of genomic, a block of metatranscriptomic, and you want to predict, I don't know, some kind of target response. And you have different block, and so multi-block partially square could deal with that without losing the information that the blocks are of different kind. So do you have any question on partial least square? Okay, so now I will explain one machine learning approach, namely random forest. So the random forest is useful when you want, for example, to build a prediction model. So as we have seen previously, you could use linear regression or partial least square, but they are only linear methods. So sometimes these methods are too simple and they can't capture some kind of relationship that are nonlinear, for example. So we could deal with a nonlinear method to see if we have some performance improvement that could be brought by this kind of method. So first, decision tree, namely a cart for classification and regression tree. So how do you build a decision tree? For example, I took a very simple toy example, even simpler than the wine datasets to explain that. So you have here three predictor variables. So the color, the diameter, and the mass, and one qualitative variable to predict the label. So you could see that that's fruit. So here we are in the classification or clustering framework, but that's the same for regression. So for regression here, you will have a continuous quantitative variable. So to build a decision tree, you generate binary questions from the dataset. So binary question, for example, is the color yellow? Yes, no. Is the diameter greater than 1? Is the mass greater than 65, etc., etc., etc. You generate all the possible questions. You choose the one that gives you the best split. So best is calculated using the Gini index and basically is to assure that you don't cut, for example, here you have two grapes. If a question uh, leads you to put one grape in one leaf and one grape in the other one, it's not good. And the goal is to have pure leaves at the end, so with 80% of the same label. And you repeat it until all leaves are pure. So for example, here, you have the datasets that I showed you before. You generate all the possible questions, and the best question is the mass greater than 65? If the answer is true, you have here a branch with three of the five individuals. You have the lemon and the two apples. And here you could see that this question has already helped to have leaves that is pure because you have only grapes here. But here you will need another question to have pure leaves because you have lemon and apple, so the leaf is not pure. And the question is the mass greater than 70? So you could see that the true question could be based on the same variable. That's on the variable mass, and here also on the variable mass. And if you use this binary question here, you have the lemon that is alone in this leaf, and here you have the two apples in this leaf. So you have your decision tree with your only two questions, and you could use it to cluster your datasets. But this decision tree have some several important drawbacks. For example, it's very unstable. For example, here, if you had only one individuals, you could change a lot the decision tree. It's also highly irregular. A small value change can affect all the tree. If, for example, here you have the lemon that is the mass of the lemon is 65. If it was 70, one of the two questions couldn't be the same. So it has a low predictive power, and also it is computationally very expensive because at each step you need to generate all the possible binary questions, and that's a lot for not here because you just have two cuts, but for big trees that could be very computationally expensive. So a guy named Brayman came with the idea of random forest. So what is random forest? What are random forests? The idea that it is very simple but could seem a little dumb is to aggregate many imperfect and unstable decision trees. So first, you don't take your whole sample. As for the cross-validation, you only drew a bootstrap sample, so 80% for the train and 20% for the test. At each node, you don't generate all the possible binary questions. You only pick a small number of variables, and you generate the question only on these small numbers of variables. So that is to deal with the problem of the decision tree to be computationally expensive. Donc you can put some restriction, but I won't give some detail on that. And so you will at the end obtain one tree with an estimated test error on this 20% dataset. That is called the out-of-bag OOB error. Out of bag because this test is taken out of the bag of the tree. And you repeat the whole procedure. So you repeat all the procedure, and at the end, you have a lot. You could have a lot. So B could be, I don't know, 1,000, 10,000. It's very fast. You could have several thousand decision trees that are imperfect, but it gives you a forest. And in fact, you could prove that if you aggregate this result, you could have really good prediction methods. For example, the aggregation could be very simple. For example, for the classification that the majority vote, if you have 90% of the decision tree that tell you that the individual one is a grape, so you say that it's a grape. For the regression, you perform the average. There are a lot of other options, for example, by averaging the results of each tree by the performance of on the out-of-bag error. But here we will deal with a really simple one that are efficient. Here you could see that you have in blue you have the relationship that we are looking for. The gray are all the decision tree. So you could see that some are very far from the blue ones. But the black one is not so far to the blue one that we want to approach. You could, on a random forest, you could also see the importance of each variables, because sometimes guys say that random forest is a black box model. It's not really a black box model. You could interpret the different variable importance directly from the forest. It is based on random permutations, and you could see that, for example, here you have a clear ranking of the variable with the most important here and the less important here. So you could, of course, it's not as interpretable as a very simple model such as linear regression, but you could have some information on the importance of the different variables. So random forests have several advantages. For example, they are nonlinear. They could capture some nonlinear relationships. They could have some difficulties if the relationship is just linear. So I think that's a good practice to always test a linear method with a nonlinear one to compare the performance. There is no overfitting with random forest. More generally, you have lot better performance than than single trees, and you have the out of bag error to compute the performance of the forest. There are different parameters of the forest, but they are known to be not so difficult to tune. So maybe no easy, but not so difficult. Um, and the forest is parallelizable, so it could be computationally very efficient. And as I said, the interpretability could be performed via the variable importance, which is based on permutations. Uh, there are some disadvantages. For example, as I said, it could perform poorly if the true model is linear. So combining random forest with a linear model, I think it's always a good approach. Yes, I said that. And as for PCA or PLS, there exist some variants where you could deal with anomaly detection, with the survival data that perform weighted aggregation, or if you want to perform some kind of sparse models. And one of the drawback of random forest, as every machine learning approaches, it needs a high number of individuals and usually more than a linear approach. In R in Python, you have different packages to apply this approach. For example, in R, you have the random forest package or the ranger package, where you could have directly the variable importance, and there is a linked package to tune the different parameters. And in Python, you have the well-known scikit-learn package to perform random forest or other machine learning approaches. As I said, there are other approaches in machine learning that could help you deal with nonlinearity if you have a nonlinearity in your data set. For example, super vector machine. So it is based on kernel, and the main idea is to separate classes by mapping data into a higher dimensional space. And the well-known neural network that could be very useful with images, but that needs a lot of training data, usually more than random forest. Do you have any questions? No, so okay. So now you should have the R Markdown file that you could open with RStudio. Uh, so you will have, so I don't know if you know RStudio, I suppose that you don't know. You will have the file that is open here with the different instruction, and here you have the explication and the instruction in R that you could copy paste here, for example, and here you could see the results. Ouais. And here you could see the result. So you could have there are some warm up for the practical application. So if you are familiar with or you could skip this part. And then you will have more questions that are linked to the my previous talk with some questions that are not really difficult. So here in RStudio, just in 2 minutes, you will have the different files that you open here. The results here. Here you could see the package that you are loading or the different files or the plots. And here you will have the data that you create. For example, here you have a matrix A. Up, you will have here your matrix A. So it's up to you. So okay, that's 4:30. So if you have some question after, you could send me an email. I will answer to you without any problem. And I hope you will keep something from this lecture. So have a nice day. Bye.